Now I want to talk about BAM, which stands for bidirectional associative memory. It's a kind of synchronous network. But Hopfield is asynchronous. But it is important to understand it before we go to a Hopfield network. So a relevant issue for the correct design of recurrent neural networks is the adequate synchronization of the computing elements. In the case of McCulloch-Pitts networks, we solve this difficulty by assuming that the activation of each computing element consumes a unit of time. The network is built taking this delay into account and by arranging the elements and their connections in the necessary pattern. When the arrangement becomes too contrived, additional units can be included, which serve as delay elements. So what happens when this assumption is lifted? That is, when the synchronization of computing elements is eliminated. And this is the magic of the brain, because if it is asynchronous, you have infinite amount of memories. You can have infinite amount of memories. I can show you, if you know real analysis, you learn about uncountable sets, countable sets. If you learn dynamical systems, then I can teach you why this is the case, that our brain can have infinite amount of memory, but we don't use it, unfortunately. Biological systems are asynchronous and spiking. Networks in which the computing units are activated at different times and which provide a computation after a variable amount of time are stochastic automate. Networks built from this kind of units behave like stochastic dynamical systems. This is the model of your brain. Forget all of the things that you hear in deep learning. It's not even dynamic, it's not even stochastic. You may say that recurrent neural networks in deep learning is dynamic, but although it isn't dynamic, but it's a very naive approach. Our biological system in our brain behaves differently. First of all, it's spiking. Second of all, it's asynchronous. That allows us to have infinite associative memory. So there is a big gap between the brain and the machine. So this is the bidirectional associative memory. First we update and we get the Y. And then from Y, we go back and we get, with the same W weight, we get the X. So BAM is synchronous. There's like a clock in your CPU, in your computer, that goes from left to right and then from right to left. So it's very unnatural. The biology is not like this. But it's important because you will see why this is important. After m iterations, the system has computed a set of n+1 vector pairs which fulfills this condition. So BAM is generalization of unidirectional associative memory. So we can write that for a set of m vector pairs, the matrix is said to be this. If you set like this, you can say many things. For example, let's define the energy function. It's XWY transpose. Remember, X is the input, the left side, Y is the right side, and this is the energy of that. So up to this point, we have only considered units with the sign function as activation and linearity in the type of associative memories we have discussed. If we now consider units with a threshold and a step function as its activation function, we must use a more general expression for the energy function. This can be done by extending the input vectors with an additional constant component. So we add two extra terms. So now we want to say that a bidirectional associative memory with an arbitrary weight matrix reaches a stable state in a finite number of iterations using either synchronous or asynchronous updates. So it's more general than just synchronous. This proposition says that it works, it converges, even if it is asynchronous. So we have this energy, and the energy can be written as either like this or like this. And then we are trying that if we change that one bit of this two-dimensional neurons, when I say, it's a pattern. So each square is a neuron. It could be fired or not. It could be 1 or 0. So if we just pick one of them and update it, then the energy will be reduced. Energy is less than the original time that we haven't changed one of the bits. This X is like many things, but just one of the coordinates is changed. So that's why we call it goes from this X to X prime, that specific coordinate is changed. So the energy of that is reduced. So as I said before, it's like Lyapunov function in nonlinear control theory, that if you have a dynamical system, the energy, if you project it in your phase space, so the energy, for example, project this two-dimensional function, the energy converges until the energy is reduced until it converges to the global minimum, for example, 0 for this Lyapunov function. But in general, your landscape can have many local, even millions of local minima. That's why when you hear a word, you associate it with many things in your unconscious mind. But depending on your mood, depending on the states of your amygdala and your brain, the weight of one of them becomes more important. So one of the patterns that is in your conscious mind becomes more important, and you forget other patterns. So brain is like a miracle. It's like a supercomputer. So we have reduced our energy at each time step, and that's it.